Now I'd like to hand over to our presenter for today, Caris Doyd, who works in our research team. She's been working for Ordnance Survey for about 4 years now, and she's going to talk to you about machine learning.
Hi everyone, so this is Caris talking. So as we said, I work in the research team in business change and innovation, and I'm here today to talk to you a little bit about some of our deep learning activities. So let's do a quick introduction first. So Ordnance Survey was founded in 1791 and is the national mapping agency of Great Britain. We collect, process and curate our own aerial imagery of Great Britain, flying it on a 3-yearly cycle using our own planes. This is about 240,000 kilometres squared every 3 years. This imagery is captured using our large format aerial cameras, which can vary between 196 and 340 megapixels, and it captures RGB colour and near infrared, making it 4-band imagery. We then process it to 25 centimetres per pixel. So finally, we also fly huge overlap in our imagery, so we can derive height models, or as we call them, digital surface models. So from this imagery, we then update our maps. So we make 20,000 updates a day to our database. And the reason I'm talking about this is because our research question is, can we use this vector database of mapping that covers Great Britain as labels for the imagery and the height data to then derive new features automatically through machine learning? So that's what we're posing. So let's get on to the machine learning bit, which is what we're all here for. There are many ways of consuming imagery in deep networks. The main 3 people use are classification, localization and segmentation. So I'm going to mainly focus on classification, but I will move on to the other 2 briefly at the end. So at Ordnance Survey, we're currently mainly focusing on using convolutional neural networks at this point. So I'm going to do a quick recap on what this means and how it works to give the beginners a fighting chance, but I will get onto the juicy details later if you're experienced in this already. So quick 2 slides on how a convolutional neural network works. And I am a research scientist and not a data scientist, so it's not very beautiful, so apologies for that. But if you imagine you've got 2 images, so you've got this triangle and this circle, and you want to put them through a model, and this blue box is going to be our model, and you want to then get an answer out the other side. So you want a label for them. You want one to be blue triangle and one to be blue circle. So in this case, it's a classification task because all you're asking for is a label for the original image. So inside of this network is a bunch of filters. Now these filters have already been trained on a task and they already know what indicators to look for within the input image to help label it. So in this case, the top filter is looking for blue things. The second one down is looking for rounded curves and the bottom one is looking for straight diagonals. So these filters aren't just placed on the image, they are smaller than it, and as the name suggests, they convolve over the image and get to see every part. And then the network will learn how to interpret how activated or excited each filter gets when it looks at the input image, and that's how it classifies. So let's do a quick follow through of that. So the triangle will feed into the network, go into the first filter, and the first filter is looking for blue things, sees something blue, and says, right, I'll give that a score of 2. I liked something in that image. The second filter, which is looking for rounded curves, when the triangle goes through that, it gets a score of 0 because there's no rounded curves in the triangle. And finally, when the triangle approaches the straight diagonal, it gets a score of 5 because it definitely saw some of those in the image. So then the circle approaches, does the same thing. Well, that circle is blue, so it's going to get a score of 2. When the circle approaches the second one, well, this time it has got quite a lot of curved edges, so it's going to get a score of 10. And finally, when it approaches the bottom one, well, there's no straight diagonals in the circle, so it gets a score of 0. So then there's a calculation, which is much more convoluted than a box that just says calculating. But when you train this network, it doesn't just learn these filters and what they should look like, but it also learns how to split data or images up based on these calculations. So in this case, if it's less than 10, it's going to call it a blue triangle. And if it's more than 10, it's going to call it a blue circle. So if we add up our green numbers, which is for the triangle, it's a 2, a 0, a 5, that's 7. Therefore, it got classified as blue triangle. And the circle in the red got 2, 10, 0, which adds up to 12, which is more than 10. So this is a really basic overview of what it's doing inside and how it classifies. But what I'm showing you here is a network with a single layer that contains 3 filters. In reality, these networks have hundreds of filters, and they can also have tens or hundreds of layers containing these filters. So this gives you many chances to learn a unique signature in your training image and therefore be a better classifier. So the reason we're calling this deep learning is because we're using models here with many layers of filters, making it a very deep network. Okay, so let's get on to the good bits. So at Ordnance Survey, we're using these convolutional neural networks to try and understand our landscape. So landscape is complex, but it is encoded in sense data, and we know that because we as humans can interpret it and we can understand it. So our sensors, such as an aerial capture, will capture this information, and then we create the neural networks to try and decode what's going on in it. And it will help us discover new descriptors, find new objects, and things we don't currently capture in our specifications. So we're working in conjunction with the University of Southampton and University of Lancaster to draw these features out from Great Britain and trying to train a network on Ordnance Survey specific things. So let's get to something concrete. So we'll start with a single use case. So roof shape. This was a hack we did in December, which was about us finding new descriptors in our landscape that isn't part of our specification. So if anyone's seen our data before, we map all buildings in urban areas to within 10 centimetres of their real world location, which is great detail, but a futuristic society is going to want even more information about those buildings, such as roof shape. So I've written down a couple of use cases that I could come up with, perhaps for solar panel placement, 3D modelling, LOD2 already needs roof shape, 5G sensor placement for autonomous vehicles. So this is a good use case for us to do a little proof of concept. So the question is, can we extract roof shape automatically from aerial imagery that we already have? So what we did was we took our polygon data, which you can see on the left. So I've coloured the roofs there in orange for you, just so you can see them a bit better. And on the right is the matching aerial imagery. So we crowdsourced labels from our internal experienced staff. They were given a polygon of the building, and it was overlaid on the aerial imagery, and they had to decide whether it was flat, hipped, or gabled. So our imagery is a perfect match for these polygons because they're captured directly from this imagery by remote sensing experts. So once they were labelled, we used FME to cookie cutter building polygons from the aerial imagery and created patches for the neural network. A patch is simply the thing that you send through it, like we had our picture of the triangle and picture of the circle that went through. They were both patches. So this made it a really simple classification task because we had one patch containing one building and we're asking for one label out the other end. So we also had the option to test out our neural network on lots of training data. So yes, we labeled them using imagery, but all of our sense data matches our database of polygons perfectly. So here we've got on the left, you can see the DSM, that's digital surface model or height model. Then the NDSM, so this is a normalized version of that. Then you can see our RGB aerial imagery. We also have RGBI infrared, but we didn't need that for the roof classification task. Then the slope, so this shows the inclination difference in the height model. And finally, Frankenband. So this was a multimodal dataset that we created. It's a 3-band image, and we put the NDSM in band 1, the slope in band 2, and the RGB imagery compressed to grayscale in band 3. and created this Frankenstein of a data set to try and contain as much information as possible about our landscape. Then on the bottom row, you can see what the patches actually look like after they had been cookie cutted in FME. So each building polygon has been used to extract just a single patch. You can see that's the same building shown in our 3 different data sets. And then it had been labeled by our team. So we trained a neural network to see which would give us the best accuracy, but we also were trying to test which of these patch types was best. And we found for this task, it was the normalized DSM that gave us the best accuracy on roof shapes. We also did 2 types of classification. So the first one was we had 3 classes, which were flat, hipped, and gabled. And the second one, we also did a flat and not flat train, mainly because binary problems are usually easier to solve, and some of our use cases didn't care about the hipped, gabled distinction. They just wanted to know where the flat roofs were. So the final question is, where should we take our training data from? Well, why is this important, where your training data comes from? This is because we need to prove that the model could generalize well. So generalization is a term for how well your model works with data that it was never trained on. So when a model is presented with brand new data, you have to see how accurate the model is in responding to it. If it's not accurate, it could be that your model is rubbish, or it could be that your model is overfitting to your training data. And in that case, we say it does not generalize well. So this is a well-known phenomenon, but how much can this apply to roofs? I mean, especially roofs in only Great Britain. And how about height models of roofs where there's no real change? Do we need to worry about this? A flat roof is a flat roof, a gable roof is pretty similar across the country, right? Well, no. So we trained in Hull only to begin with, and then when we deployed it in Cornwall and Basingstoke, you can see that it actually performed significantly worse. So the green is the amount it got correct, the red is the stuff it got incorrect, and the grey didn't meet our confidence threshold, which was at 80%. It's worth noting that in Hull, it was getting 91% accuracy and was labeling almost all of the data. So why is this? Why did this happen? Well, let's have a look at the data. On the left, you can see the data in Cornwall, and on the right in Hull. So here we're looking at flat roofs, and you can see the Cornwall flat roofs are grey, or they have sort of a mixed, murky appearance to them. Whereas where it was trained in Hull on the right, they were usually white. So maybe it was this difference that meant it failed to generalize. Hull roofs that are flat just don't look like Cornwall roofs. So then we had a look at the hipped and gabled data set. So in the left in Cornwall, you can see most of the houses are hipped. They're also less tonal colours, more neutral. And in the right in Hull, you can see there's a load of bright orange roofs, which is not the same as the Cornwall ones. They're also mainly gabled. And finally, there's a lot of shadow from the imagery on the top of the roofs, making them look different. So lesson 1, choose your training data wisely, because you will waste a lot of time working out why things have gone wrong when it's just that you needed to generalize. So what we did next was we hand labeled a load more roofs from all over Great Britain, and we solved that generalization problem. So we've curated a new data set at this point, not just Hull. Then we use CNTK, which is Microsoft's toolkit as a backend. And we tried ResNet 34. The reason it's called ResNet 34 is because it's 34 layers deep, each with hundreds of filters in it. So ResNet's famous for winning most of the image classification competitions in 2015. I think it pretty much won them across the board. So it seemed like a safe bet for us to try. So here you can see the results of us trying three classes, hipped, flat, and gabled, and we got an accuracy of 85%. So as I said before, most of these use cases are agnostic about the hipped and gabled distinction. So what if we just tried flat or not, made it more binary? And here you can see we got 91% accuracy when it was just flat or not. So there is a little run through of a single use case and how this has been successful. But we're actually being much more ambitious than that. So next I'm going to introduce you to our main overarching research project, which is called ImageLearn. So our plan is to move away from the archetypal deep learning model that I just explained to you, where you label data, train a model, and solve a specific task, because you just have to rinse and repeat that for every other problem. So instead, why don't we try and shortcut that cycle and pull out learn features in a different way? So we're trying to train a deep network to decode this landscape and help us understand what's known as the underlying explanatory factors hidden in our landscape from Bengio's paper. But what does that mean? Well, we know patterns make up our landscape, and we know us as humans are good at decoding some of these. Deep learning algorithms are also really good at detecting these patterns. But when we train a neural network, there are thousands of filters that are learning exciting patterns within our imagery. And each one is not just learning the features you're asking for, but it's learning all the detail that goes into making that thing up. The parts of the object, the surroundings of the object. So for instance, if you had a model trained in finding birds, it probably also has filters dedicated to finding beaks and feathers and nests and trees and skies and eggs, as well as the bird itself, because these are things, details that are common to being around birds. So we as data scientists are asking the network to learn all these things, thousands of things, and then telling it to condense it back down just to the two things I asked for. So in this case, a logo or not a logo, which seems a bit wasteful. So here's an example with our data. So our database is on the left. You can see it's just topography I've pulled out here. And on the right is the matching imagery. So in that blue box where I've zoomed in our database of topo, we have the classification of made sealed surface for that center polygon. We also have a functional site that says sports facility. We do label tennis courts, but the network never saw this. It only saw the topo, which says made sealed surface. It's the only label it was given. But when we look at the imagery, we can actually see much more detail than that. The neural network is convolving over this entire image, and it will also see all that detail, and it might learn tennis courts as one of its patterns in a filter. There may be a filter there picking up tennis court patterns. But then it will then have to condense it back down to the few classes that I asked for. So it will then call tennis court patterns made sealed surface because that's what I told it to do. But nevertheless, that pattern has been learned. Okay, so let's take one more example. Our database here would contain the topography of made sealed surface for that road in the center of my blue box. We also have real world terms that would say road. It would also have a name. But again, the network won't have been trained on that. It will simply see made sealed surface as a label. But when we look at the imagery, we can see much more detail. We can see white lines going down the center of the road. We might see drains. We might see drops in the curb. So what if these patterns are learned too? That's one of our research goals here at Ordnance Survey. So just quickly go over our goals. We're doing this in conjunction with the University of Southampton and the University of Lancaster. They're helping us with this, and they actually trained and fine-tuned our first model. So the first goal is to infer the presence of real-world objects that we don't currently record. So I just showed you white lines and tennis court patterns, but there's also manhole covers and street furniture, and roof types and roof materials and age of buildings. Okay, so those are real-world things that we don't record, but we could. And the second thing is to discover new descriptors for our landscape. So these are more conceptual things that may also be useful, such as eras of building development. Could it identify Victorian housing estates? We know that our remote sensing experts can, so perhaps it could start picking up on those sort of descriptors. Also environmental zones, patterns of vegetation, who knows? So we're currently ramping up to start to ingest a lot more imagery in our neural networks. So we actually, just clockwise from the left, now capture and maintain handheld camera imagery, digital surface models, so that's height. That's the Frankenband or the multimodal data you can see there. Then angle of slope, RGBI imagery, vehicle mobile mapping imagery, vehicle LiDAR point clouds, and then oblique So it's just some of the data that we have to play with here as data scientists, and we can use any of these. But we thought we'd start off to begin with training our OS master map topography layer against imagery, as this is what our remote sensing experts capture through. So it makes sense that these patterns should be easily distinguishable. So we stuck it through ResNet 50. We used 22 classes from topography. So we condensed it a little bit. I believe we have around 2,600-ish labels in the topography layer. So 22 to begin with seemed like a good starting point. And when we output this model, which was fine-tuned, by the way, so that means we used ImageNet weights and fine-tuned it to the Ordnance Survey signatures, we got 78% accuracy. So, you know, that's good, that's exciting, that's 22 classes with almost 80% accuracy. But more importantly, when we looked inside of the black box of this model, we started to see patterns emerging from this imagery that we realized could be useful. So these images are actually showing you filters within the network and the top 16 things that they found exciting. And there are actually thousands of these examples, so I just picked out a couple. And as I said, this was only with fine tuning, so this is not even training from scratch. So the top image you can see has got grass. It's definitely picking up grass features. The next one is picking up white vans and greenhouses. And then along a bit, we've got blue cars. And then the second row, we have tarmac. And then we have roads with curbs, and then finally hipped roofs. And then the bottom row, we have red cars, roofs, and red objects. So we can start to use this deep network as a feature extractor and gain more from it this way when training it on a shallower network. So we didn't ask for any of these things. We trained it on basic topography, and these are the patterns it's picked up. So how do we use this shallow network to pull out more exciting features? Okay, so in this case, we fed pictures of playgrounds and non-playgrounds, and we were trying to check against our OS green space product to see if we could either do a QA from it or just test something out where we already knew playgrounds were, just to test this scenario. So you should note that this network was never trained on playgrounds as a class, but instead it started to recognize the patterns within the filters. So you take the image of the playground, you run it through your deep network, you use the layer outputs, not the classification, the layer outputs, as an input into a shallower network with a label, playground, not playground, and then you see how well it does. So in this case, with the fine-tuned network, we got 92% accuracy on playgrounds, and the scratch network gave us 91% on playgrounds. So we're proving that it is picking up these details, and we can use these deep networks as a feature extractor for mapping aerial imagery. So one question I might get later is, why was the scratch trained weights worse? We think it was the class choices, which didn't allow the ResNet 50 model to pull out the full hierarchy of features as we wanted. So we are literally this week training again with new classes to test that theory out. So you might have to get back to us for that one. So this is one way we can harness the power of all those filters. So we've done a deep learning classic where we did the roofs and we used the outputs as a classification. This is us using a deep network as a feature extractor. And one final topic I want to cover was these are both classification tasks. So what about localization and segmentation? So OS is currently doing another research sprint to find windows and doors in vehicle captured mobile mapping imagery. So why are we doing windows and doors? Well, I listed a couple of things here that it could be useful for. So for one, it's an intermediate step into creating new data sets like numbers of floors or access points. But also it's needed for things like LOD3 modeling of buildings and can just be useful in of itself. So we're labeling imagery currently with bounding boxes of windows and doors and drawing on the expertise of John Slade, who's one of our sponsored PhDs at Cardiff University, and testing our crowdsourcing with this using bounding boxes and labels. And we're gearing up to test computer vision techniques as well as deep learning techniques, such as localization, where we'll be using the bounding boxes, and possibly even segmentation. We're going to try lots of different techniques until we find the best solution for this problem. So here you can see some of our data that's been labelled with the mask R CNN labels from Her's paper when he was at Facebook. So we're going to build something pretty similar to this, but for labelling windows and doors. But I'm afraid you're going to have to tune in next time to see how well we got on, and we'll keep you posted. So in summary, Ordnance Survey is investigating methods for providing more detail to offer Great Britain. We're trying to enhance our data sets, and we're using cloud classification deployment. And overall, we're trying to provide more detail in this mapping as needed for the new technologies like autonomous vehicles and 5G and LOD 2 and 3 and even BIM. So I've taken you through how we're using deep learning with convolutional neural networks to classify data, but also how we're using deep learning as a feature extractor for a shallow network. And finally, how we're using deep learning to localize and segment our imagery for windows and doors. So that's it. Thank you very much for listening. And I hope that gave you a good little taster of what we've been up to. And I'll see if we have any time for questions. Okay, so one of the questions is, will the results feed into master map data or will it be separate? So that's actually something we're debating here at Ordnance Survey at the moment. And some of these things will fit very well into master map data, especially if we're adding an attribute to a previous polygon, such as with roof shape, that might be run in the future and added into master map. Some of these things might actually be discovering new descriptors that don't fit well into our master map solution. So we may be adding more layers as time goes on. Good question, and keep you posted because it's something that we're debating here at Ordnance Survey as well. So one question is, you have highlighted very well how training data is key to the success of deploying your models more widely. To what degree are you able to keep feeding new training data as you top things up? Right, so for the roof challenge, we labelled many thousands of roofs, and we could have just put in as many as we wanted. We actually found we reached a sweet spot where we didn't need to label anymore, and we were getting sort of 90% accuracy, which was good enough. But actually what you can do with these networks is, if you're finding you're getting bad results on some images, you can then find one similar to that image and train your network on those in its next training batch, and hopefully start to solve the problem that it has with some of those. We also, part of that question was about how you keep it topped up. So with our other training, with the master map topography against aerial imagery, we, in terms of size of amount of pixels we have trillions of pixels to train on against our topography layer. And that's before we start to bring in classifications from our functional sites and from our building heights layer and from our water networks and all the other layers we have. So in terms of ImageNet, we massively have way more data basically than is in the ImageNet dataset. And we already know that ImageNet is getting things like almost 100% on some of these classification tasks. So, good question. Someone's asked, what do you do with eccentric roof types like domes? So when we trained this, oh, and yes, someone has also asked about loft conversions as well. So, so what do you do about these crazy roofs? When we trained the network, when we labelled them, we did actually have some that were being labelled that weren't tipped, gabled and flat. We didn't actually keep our remote sensing experts on just labelling those three things. So we ended up with sawtooth and dual pent roofs, and the thing is, we just didn't have enough of them. So with curved roofs, I think we ended up with about 30 that had been labelled, whereas we had thousands of flat and hipped and gabled. So we decided to not use it for this classification, as it seemed most of our tasks wanted flat or not flat roofs. If ever we were to deploy a very detailed roof layer, we would have to take into account that there are some crazy roofs out there, like especially on churches with church spires and things like that. But for now, those three classes felt like they were good enough for the use cases. Okay, someone's asked, what platform are you using for the machine learning? So we're currently using Azure as our cloud platform. We do mini runs on our own computers here where we have NVIDIA GPUs. We then deploy to the cloud for our big training runs. We've experimented with many architectures and many backends. We've used Caffe, TensorFlow, Keras. We're now looking at PyTorch. We've done CNTK. And I'm probably missing a load, so apologies if I am. So we're just experimenting. We're pretty much agnostic. It's what gets us the best result. Ordnance Survey is known for its detail. It's known for getting things accurate, and so we must, as the deep learning team, match that accuracy by whatever means possible. So we're not stuck in a box in that. We're happy to go wherever to get the results that we need.